Welcome back to ECE 320A. Homework number 10. Don't tell anyone, but that's due on Thursday. You can know that. I'm doing that to give you more time. We really haven't talked about the second part of that assignment, and that's what I want to cover today. Here are some office hours that are scheduled between now and your final exam. If you have already filled out your online teacher course evaluations, thank you. If you haven't, please try to do that in the next day. Those close on Wednesday. You will not have any more opportunity to fill those out until, well, you won't. It'll be done after tomorrow. And I do not see those results until sometime in January if I'm lucky. So it's way after your grades are posted. So don't think that that's going to influence or impact your grade in any way. The review session for the final exam is scheduled for Thursday. A lot's happening on that reading day, but that's in the afternoon from 2 to 3:30. If you have any questions, burning questions that you really hope that I would address during that review session, you may email those to me and I can try to integrate some of those or all of those depending on how many questions I get and how I can consolidate those. If you have some questions that are really bothering you or you really want to try to get well understood before the final exam is on Tuesday and it's from 10:30 to 12:30 in this room. Hopefully that comes as no surprise to you, and I hope that date is correct. That's the 17th of December. The process for the final is consistent with what we've been doing all along. I'll allow you to have one more sheet of notes. Maybe you'll have some formulas for two-port circuits on that in terms of the Z parameters and how you might solve for those Z parameters or what the equations might be if you had an interconnected circuit that contained Z parameters, and we'll try to talk about those today in class. Hopefully, if the recording works, we will have notes and video of the review session if you are unable to attend on Thursday. And there already is online on the D2L website a practice final, and the format's a little different. It's multiple choice. So you might look at that just to get familiar with it. I'm not sure the format that will happen this semester, but that's what happened that semester. That was many years ago. The reason I'm posting that, usually I don't post finals, is I had someone, I think it was a plant, in the class. I handed it out and I said, "Are you in this class?" "Yeah." I started walking up the stairs and the student exited very fast. So that final is out there. I just decided to let everyone see it. I don't know how much he made off of that grab, but I started taking out after him, and then I said, I have a classroom full of students with finals on their desks. I better not be doing that. But it's a good thing I didn't catch him, actually. Wouldn't have been pretty. All right. So what do we want to do today? We want to finish up the filter example that we had semi-finished last time. We derived the normalized third-order Butterworth filter. Let's just see how we could then translate that into a maybe more practical situation where we have a specific bandwidth, not just fixed to 1 radian per second. And then we'll discuss all of Chapter 18, well, parts of Chapter 18, enough to hopefully get you comfortable working the problems that you have on the homework number 10, and final exam questions that might be related to two-port circuits. Here is what we had last time, and you might just double check the structure of the second order section. For some reason, I was not sketching it very well. Actually, I was sketching it incorrectly. So make sure that it's sketched properly. I think I had, the resistors going into the inverting terminal. Make sure that it's consistent with the figure in the text, but this is now how you can build higher order filters. If you had a fifth order filter, you could simply put another second order section in front of this, and then you have a fifth order filter. Now, the parameter values might be different, and that's what determines, or those are determined by the tabular entries, or if you sketch the Butterworth pole pattern, those poles then impact where these normalized R's and C values will be, depending on the filter order. In this case, we needed our denominator for the second order section to have a polynomial, a second order denominator, since it's a second order section, to be s squared plus s plus 1. The b1, it's not maybe obvious, but it's right there, and it's sitting there as a value of 1. B sub 1 in that particular, when we have a third order Butterworth pole pattern, we want our three roots to solve that product of terms. And that will give us then one pole at -1 and two poles separated by what angle from the real pole. So we have 360 divided by 2 times the filter order. So it's 360 divided by 2 times 3, or 360 divided by 6, or 60 degrees. So the roots of this are going to be 60 degrees away from this pole at -1. And if you do the factoring, you'll get -1/2 plus and minus j, the square root of 3 over 2, I believe, for the roots of this quadratic, s squared plus s plus 1. That comes from the table, or it comes from your sketching. And then you know, since this particular spot was the location for B1, in our derivation of how to find the parameter values for a quadratic corresponding to that particular second order section realization, here we can see that B1 is actually 1. C1 was 2 over B1, so in this case it becomes 2, and C sub 2 is just the reciprocal of C sub 1. And the first order section, which gives us that pole at -1, our R's, R1 and R2, are both equal to 1, and our C value is equal to 1. And hopefully it's clear what parameters I'm defining by R, C1, C2, R1, R2, and C. Is that clear? Because now when we start to change the frequency or the bandwidth of this low-pass filter, right now this is a low-pass filter. How big is it? What's the order of that filter? It's not that hard, is it? It's a second order and a first order. It's third order. What's the bandwidth of this filter right now? If we realized this filter, what would be the low-pass frequency's bandwidth? What's the half-power frequency, or what's the -3 dB frequency? 1 radian per second. What we typically want to do is something different from that, but this now represents a third order low-pass Butterworth. Butterworth just defines those pole locations. You could use these same circuits and have different pole values by a different choice of R's and C's. We've picked those R's and C's to get us a Butterworth filter. And what's so significant about a Butterworth filter? Pardon? There's no ripple. We didn't really even speak of ripple, but there's no ripple in the pass band or in the stop band. But if there's no ripple, there's no bumps on our pancake, it's flat, isn't it? And it's flat as far or as close to the cutoff frequency as possible. That's maximally flat. That's how we define this Butterworth pole pattern characteristic. That's what the Butterworth gives us. It just gives us the pole locations. We've agreed that that particular third order realization, that circuit, had a bandwidth of 1 radian per second. What if we wanted a bandwidth of 200 hertz? What do we do now? Then what? Do you remember? I'm climbing a, no, I was scaling a mountain. So we need to scale. We need to scale something. If you're just listening to this, you have no idea what I'm talking about. I'm just doing all sorts of crazy things in class, so unfortunately you missed it, right? But we now need to frequency scale with this parameter K sub f. K sub f is the ratio of the new cutoff frequency compared or ratioed with the old frequency. That defines our frequency scaling parameter, which we had defined to be K sub f. In our case, we need omega nu not to be just 200. It needs to be in the same units as omega old, and omega old was in radians per second. To be consistent, then, we need to have omega nu to be 2 pi f, or 2 pi times 200. Omega old is just the 1, which says now if we need to frequency scale any of these parameters, the r's and the c's, that's the K sub f that we use. If we frequency scale the r's, how do they change? Trick question, wasn't it? They don't change. Our resistors are not dependent on frequency. If you looked at the impedance of a resistor, it doesn't have an omega floating around like the L and the C do, does it? So the resistors, if you're simply frequency scaling, you don't have to adjust the resistor values. Yes? Pardon? Yeah, I don't know how I dropped a pi. I don't normally miss a pi. Oh, but maybe this pi I might. But if it was a real apple fruit pie or something, I wouldn't have missed it. Yes, thank you. That should have been 400 pi. And it shouldn't be hertz, should it? Man, you got me thinking about pi, and look out. So this is now, I'm just making sure you're paying attention. Is that okay? Are we better now? And what am I doing? Gosh, you guys, K sub f is dimensionless. I just canceled all my units. My notes are correct. I just am getting so excited. I was scaling mountains and everything else up here. So now we have a frequency scaling factor, K sub f. It's just 400 pi, right? When we change capacitors and inductors, we better not change the units when we scale them. So that's a dimensionless parameter of a value of 400 pi. Well, this will now be a little bit boring if we don't have to convert the resistors. So let's just also make another assumption. Let's suppose that we also I'll let you in on a little secret. Somebody spilled coffee up here, and all I can smell now when I bend over is coffee. Man, didn't get enough for lunch. Suppose we also, coffee's not going to cut it though, is it? I don't drink coffee, but it smells good. Okay, suppose we also want the R's to be 10,000 ohms. What's that mean? Have to climb another mountain, don't we? We have to scale again. This now says that we have a K sub m, and we can find that now because we know what the new R's need to be, and they were all the same before. which allows us to just say, oh, all the R's, change them to 10K. R old was just 1. R new is 10, and now then we have a value of K sub m of 10,000. We can now find parameters or resistors and capacitors that will implement a 200 hertz low pass third order Butterworth filter by using these new values of R's and C's in that previous circuit diagram. By relating or making R bar be 10K, the bars now are the new, since I already have 1s and 2s floating around. The bars are my new parameters. And I started with an R, so now the R bar value is 10K. The R sub 1 bar is 10K, or that's K sub m times R1. That's all I'm doing. And the R sub 2 bar is also 10K, because they all started out being 1. My C's are a little bit different because now those are, let's say, C1 over both of those scaling quantities. K sub F over K sub M. C sub 1 actually was 2, and if you plug in all of those numbers, you end up with 159.2 nanofarads for the modified or the scaled C sub 1 parameter, which we're now calling C1 bar. Meaning that would be located right there. That's now our C1 bar. It would now be 160 nanofarads instead of 2. So we might be able to find something in that range a little easier than putting 2 football fields on our small circuit board. 2 farad capacitor. We have supercapacitors now, so that's not quite as bad as what I just said. But now we have C sub 2 bar. That's this 1/2 over these 2 parameters, scaling parameters. And that now becomes 1/4 of 160, or about 40. This is now 39.8 nanofarads. And finally, we had one more capacitor in the first order, or the first order stage on the right, and that had a value of 1. We divide 1 by all of those, and we end up with 7.96 times 10 to the minus 8 farads, or if we're going to keep units of nanofarads, we're up to about 80 nanofarads. So we have a 40, an 80, and a 160 nanofarad capacitor. And that really completes our design. How fast in the high frequency range will this filter roll off? What's the slope at high frequencies? What do you need to know to answer that question? This is a final exam question. You just need to know the order, don't you? It's third order, and each one of those contributes 20 dB per decade down. So it's minus 60 dB per decade is the slope, or the roll-off rate, into the high frequencies. What's the cutoff frequency? In radians per second, it's 400 pi. In hertz, it's, isn't it 200? Is that what we wanted? 200 hertz. And we know the magnitude of that transfer function at that cutoff frequency is 0.707, or 1 over the square root of 2. What's the phase of this filter at high frequencies? We do not have any finite zeros, do we? So the numerator is not influencing our phase. We'll just assume that the sign of this is 1. It could have been a negative, but let's just assume that we're worried about nothing in the numerator. Then what's the phase at high frequencies? If I had asked you to sketch the Bode plot for this, could you do it? That's basically what I'm asking with some of these questions. What are some ways of checking your result? Where's the phase begin? At low frequencies, what's your phase? 0 degrees, right? Because we had nothing in the numerator, no s in the numerator, and our s's were all in the denominator. But if we let those be small, the only thing remaining was a 1 down there as a constant. So we have 0 degrees minus 0 degrees. It's 0 degrees, and then each of those 3 poles contributes minus 90, and so we end up at high frequencies with a phase of minus 270 degrees. Is that okay? Enough for filters. Let's now look at two-port circuits, which is chapter 18. And now you know we have to put on our 2-year-old hat and ask why. Why two-port circuits? How many are taking 351C or have already had 351C? Have you had hybrid parameters? H parameters? What? HFE, for example, H sub FE. Have you seen that floating around? That's this guy. Or you could see two-port parameters, the H parameters, hybrid parameters. We're going to focus on Z parameters, but what we are doing is trying to collapse down or simplify a complex circuit into maybe 4 parameter values, or describe some piece of a subsystem or a circuit by 4 parameters. Meaning, if you have a complex design, it might be easier it's just like eating an elephant, right? One bite at a time. You break it up into smaller pieces. So that's what we're doing here. We're simply breaking up this complex design into smaller pieces, and these smaller pieces might be sizes or chunks of two-port circuits. It might be easier to attack the design in pieces. Meaning, we might have a design where we have maybe a photodetector, and we want that when it responds to maybe drive an actuator. But it can't, a little photodetector is not going to be able to move a big electromechanical actuator. So we may have to do some signal processing and amplification to make that happen. Meaning we might have to amplify this small signal coming from the photodetector with a preamp. We might not be wanting to dance around with every little signal that the photodetector detects. And now maybe we put a low-pass filter in there. And you know now how to build low-pass filters of any order, of any complexity, especially Butterworth. Then we might want to, boy, I'm going to run out of paper width, but you know how I solve that problem. Now we might have to power that up in order to drive this actuator. instead of having to worry about building all of this up in one big piece, we could think of each of these three little subsections or sub-circuits in terms of its two-port parameterization. And now we simply have to design a low-pass filter. We simply have to design a preamp. We now have to design a power amp. And then we put all of these pieces together, and they sing very well together so that we can now respond to whatever that photodetector is measuring and driving this actuator. What are these things called two ports? Two ports, schematically or as a picture, look like what we are stating they are. We now have this system or circuit, and it has a port on the left, which we might call the input port. We have currents going in and the same current actually going out, I1, and we might have then a voltage across those two terminals, V1. And that might, in some particular system, be representative of an input. We could also then, or conventionally, we have I sub 2 going in from the right to the left, and it also needs to come out of that port. Meaning here is our input port, the 1s, and the 2s with subscripts are the output port. And we might have 1,000 transistors and R's and C's inside that S, and we're collapsing all of that down into maybe two parameters that characterize this system in terms of these two ports, an input port and an output port. That's what we're wanting to do, and all we are really wanting for now is to be concerned with the terminal or the port behavior. We're only interested, we've now designed it the way we want it or the way we like it, and now we're only interested in the terminal or the port behavior. With respect to two ports, we have actually some restrictions which, when satisfied, allow us to play with two ports. One is we do not allow any energy stored in the network. No energy stored, so we don't have any batteries in there. We can have energy storage elements in here, but no energy stored within the network. Basically no active, or well, I shouldn't say that. No, let's just think of it as no batteries inside that subsystem. We also are not going to allow any independent sources. So we don't have any function generators inside that big block S. No independent sources. Within the network. But dependent sources are allowed. The diagram already illustrated this, but our currents, if it goes in to the top terminal, it has to come out the bottom terminal. So our current into a port must equal the current out of that same port. and you might hear this referred to as the port current requirement. And finally, if we interconnect this two-port with something else external to it, all of these external connections are made to either the input port or the output port. All external connections are made to either the input port or the output port. Those are our restrictions or constraints to allow us to use these concepts of having a two-port, and you don't have to worry too much about those, but that's just something to keep in mind for later. In this particular description, how many variables do you see? Oh, so don't double count. If I have an I1, don't count it twice if I have it up there twice. How many unique variables do I have? 4. And we are going to allow 2 of those to be independently selected. We have 4 variables, and 2 of those we will allow to be independent. That means for a two-port, we really only need 2 equations to describe the behavior of that circuit. Because we're going to have 2 independent variables, 2 dependent variables, and we only have the 4. So now we have 2 equations that are going to be governing this behavior. We have 2 equations are needed for the different possible interrelationships that we might have. So if you're looking at your textbook sometime, page 680 is where 6 of these two-port equations are listed. We have Z parameters, those are impedances. We have our independent variables are the currents I, and the dependent variables are our voltages. So that's like having an impedance there between the currents and the voltages. The second set, equation 2, is the reciprocal of that. We have voltages as inputs and currents as outputs. So those are our admittance parameters. The first ones were our impedance parameters. And you can walk down through this. The second or the third set looks like you have all of these output port variables, the V2 and the I2, driving or determining your input parameters. And those are like transmission parameters from the output transmitting back to the input. Similarly for 4, now we're going from the input transmitting up to the output. And you might see these kinds of parameters in like a 381 class, for example, an electromagnetics class. There's the H parameters, and that's a hybrid. It's mixing input current and output voltage to drive input voltage and output current. And then you have sort of its twin or its complement in the G parameters. Those are the different configurations. We are going to be concentrating on those, the Z parameters. So you don't have to have all of these memorized. You just need to know what's going on, and that's the one that we are going to be looking at. So hopefully you didn't stress out by trying to write all of those down. in the short amount of time that I gave you. Let's look at some examples trying to derive these or find these for particular circuits, which is what you will need to be doing on the homework and on the final. Here is a particular structure that might be called a T-network. It's now called that because of the way it's physically structured. It looks like a T. Here is now our variables that we have defined for the different locations of current and voltage. And if I1 is flowing there, and let me go ahead and label these resistor values, we have a 1, a 3, and a 2. We could think of these currents, I1 and I2, as somewhat like mesh currents. They're not going to be flowing in the same direction like you typically want to define mesh currents, but you really have this current is I1 and this current is I sub 2. Is that okay? Meaning the current going down through that middle path is a combination of the input and the output current to give you I1 plus I2. What we want to do is find the Z parameters for this particular T network. And if we remember what we just saw in that list of equations, the Z parameters say, oh, that relationship is V1 is Z11 I1 plus Z12 I sub 2, and V sub 2 is Z21 I1 plus Z sub 22 I2. And the indices or the subscripts on your Z's hopefully are somewhat clear. The second one is saying, what are you taking? And the leftmost one is saying, where are you going? Or input and output. So Z11 is the impedance between I1 and V1. Z sub 12 is the impedance between I2 and V1. All right, if you had to analyze this circuit, how would you do it? Just a normal circuit problem. And in this case, V1 might be potentially a signal source. There might be a source there, so you could sort of view that as having a supply in V1. And V2, that might be an open circuit. It might have a load attached to it. It might be a short circuit. And so you're measuring these V1 and V2 potentially in a given configuration. But now we want to find equations that, and in another setting you could say, oh, let me have V1 as a source and V2 as a source, and write the equations. How would you solve that? Or how would you analyze this circuit? It's sort of begging to do mesh analysis, isn't it? We've got two meshes. Why don't we use something that we're comfortable with using? If we write a mesh analysis equation for the left mesh, so let's do now KVL at the left mesh. Now we just have to remember how those currents are oriented. They're not both going clockwise or counterclockwise. One's going opposite to the other. We have in the left mesh, we have minus V1 plus 1 times I1 plus 2 times I1 plus I2. Is that okay? That's just KVL, and you should be very comfortable with that at this point in this course. So we have minus V1 plus 1 times I1 plus 2 times I1 plus I sub 2, and that brought us back to where we were going, or where we started. we want to find or identify Z11, Z12, Z21, and Z22. Well, this equation has a V1 in it, and it has I1 and I2 in it, doesn't it? But the first thing we might want to do is say, well, how would we find Z11 in this first equation? We could find it if we set I sub 2 equal to 0 pretty easily. So if we set I sub 2 equal to 0, then if we could find a relationship between V1 and I1, we would have our Z11. Meaning now to find Z11, we need to find 4 of these parameters. Let's find that by this relationship. Let's go ahead and set I sub 2 equal to 0. If we do that, now we have minus V1 plus I1 plus 2I1 is equal to 0. Or V1 is equal to 3I1 and Z11 is 3. Or Z11 we really found by taking the ratio of V1 to I1 when I sub 2 was equal to 0. And that ended up being 3. Does that make sense? There's Z11. Now you have 25% of the problem finished. What if we wanted to find Z12? Do the same strategy. We have the governing equation. If we now want Z12, what happens when we set I1 equal to 0? Now we have minus V1 plus, whoops, that was a 0, wasn't it? So we had 1 times 0 plus 2 times 0 plus I sub 2. Or V1 is equal to 2 I sub 2. And that now allows us to say, oh, we've now found Z12. V1 over I2 with I1 equal to 0 will give us Z12, which in this case is 2. Questions on that? What about the other 2 parameters? Well, that worked so neatly for that one. Why don't we just write a KVL on the right-hand mesh? Now we have a minus V2 plus 3I2 plus 2 times I2 plus I1. That's our KVL for the right mesh. Now we have minus V sub 2 plus 3 times I sub 2 plus 2 times I1 plus I sub 2 equal to 0. And if we want Z sub 2, 1, then that's the impedance between I1 and V2. We can set I sub 2 equal to 0 in that relationship. And doing that, we now end up with V sub 2 is equal to 2I1. Or Z21 is now V2 over I1 with I sub 2 set equal to 0, and that's equal to 2. And finally, to obtain Z sub 2, 2, with that second mesh equation, we can simply set I1 equal to 0. And now we have minus V sub 2 plus 3I2 plus 2I2 is equal to 0. Or now we have Z sub 2, 2 is this V2 over I2 with I1 equal to 0, and that's now equal to 5. Meaning our z parameters, if we wrote this as v is equal to zi, which is really what it is, with v being a stacked vector, v1 over v2, and I being a vector, I1 over I2, the impedance matrix, or the z parameters, are z11, which hopefully was 3. The off diagonals were equal, and they were 2, and we had a z22 of 5. And those are the 4 z parameters for that T network. And those don't all immediately appear as separate elements in that circuit. We have a 2, that's what's common to the 2, those are the off diagonal, but then the others are really the sum of those 2 impedances seen by I1 and I sub 2 in this particular circuit. Let's get a different circuit. Suppose now that you are finishing this second circuits class, we need to be a little bit more challenged with the circuit analysis. This shouldn't challenge you too much. This shouldn't take you much more than a napkin to work. We now have R1, R sub 2, R sub 3, and let's say this is now beta V1 here, and that's, let's say, a controlled current source. Here's V1, here's V2, there's I1, and there's I2. And again, maybe what we're looking for are z parameters. Independent of whether or not I ask for the z parameters, if you had to analyze this circuit in terms of V1, V2, I1, and I2, do you have a feel for what you might try to do? What kind of analysis you might try to perform? Now that dependent current source is problematic if we tried to do KVL or mesh equations, isn't it? Because we don't know the voltage drop across that. So maybe we need to write KCl equations or node voltage equations, and we can now define some node voltages. Let's just call this one as V sub A, and that one is V sub B. And what we want to do now is simply write KCl equations at nodes A and B. At A, what's our KCl equation? I'll do the hard part. I1 is equal to. Now we know the algebraic sum, or currents in equal currents out. What's the current going vertical? And then we have a horizontal current. That should be comfortably derived for all of you, right? That shouldn't be a problem. What about the second node? Again, I'll do the most difficult part since it's late in the semester. I2 is equal to. Now we have a voltage controlled current source, but that's just given. That's beta V1, and then we have the horizontal current going in the other direction. So that's now VB minus VA over R sub 2. And I might sit down and put my feet up and say, oh boy, I'm feeling really good? Am I premature in that good feeling? What am I looking for? Z parameters, which are equations that should contain what variables? My equations were V1 is something I1 plus something I2. V2 is equal to something I1 plus something I2. Ah, those silly V sub A's and V sub B's. I got some extra variables in here, don't I? If I need to get rid of those, if I could rewrite V sub A and V sub B in terms of I sub 1 and I sub 2, I'd be in pretty good shape. And that's what I want to do. I need equations which contain I1, I2, V1, and V2. Consequently, I need to get rid of V sub A and V sub B. Or I need to rewrite those in terms of I1, I2, V1, V2. If I go back to this picture, this circuit, what do I know about V sub A and maybe V sub 1? They're exactly the same, aren't they? So I could have eliminated V sub A from the beginning, but here are some observations. One is that V sub A is simply V sub 1. Well, that was pretty easy. I can now relate maybe V sub 2 and I sub 2 to V sub B by finding that current for I sub 2. Meaning I sub 2 is equal to V sub 2 minus V sub B over R sub 3. And that now allows me to solve for V sub B. V sub B is now V sub 2 minus R sub 3 I sub 2. And now I'm in better shape. Now I have equations for VA and VB in terms of I1, I2, V1, and V2. So now I can rewrite those earlier equations. I can now say I1 is V1 over R1 plus V1 minus V sub B, which is now V sub 2 minus R sub 3 I sub 2 over R sub 2. That gives me one equation. This was simply the V sub B from before. And in that first equation, all I have are V1, V2, I1, and I2. And that's what I needed. My second equation, I sub 2, was beta V1. That was okay to begin with, but then I had a V sub B, which is just V2 minus R sub 3 I sub 2 minus V sub 1 over R sub 2, and that's my second equation. Now I have two equations with four variables, but I'm looking for Z parameters, so I now need to find V1 and V2 in terms of something times I1, I2. If I look at this, hopefully you can see that I could start pulling out V1 and V2. I could put this into sort of a matrix structure, and you're all experts with that since you're in 310, right? This now says that I have some matrix times V1, V2 equaling some function of I1, I2 on the right. I can simply put all the i's on the right-hand side, and then I have another function down below for the second equation. I hope that's okay. Then I can simply invert that squiggle, that matrix, and I'll have my equation that I want. If I invert this guy, I can now solve for V1, V2 and obtain my Z11. It might be a function of S, Z12 in the general case, and that's now going to be my Z parameters. I want to give you some fun, so I'm going to allow you to go home and do that tonight. And you can then verify that Z1 is R1 over 1 plus beta R sub 1. Z12 is the same. And with my track record today, these may not even be correct, so you can come see me in office hours to verify if you're not coming up with these equations or these formulas. Z21 is now R1 minus beta R1 R2 over 1 plus beta R1. And then Z22 is the most complicated of all. It's now R sub 1 plus R sub 2 plus R sub 3 plus beta R1 R3 all over R2 times the quantity 1 plus beta R1. And those are now our Z parameters for that circuit. And that circuit had a dependent source in it. But the process should have been clear as to how we derived it. We just started with some basic KCl equations, and that led to this result. That's now how to find the Z parameters if you're doing circuit analysis. What if you go into the lab and take some measurements? Can you now extract your Z parameters from some physical measurements? Let's now find two-port parameters. Finding two-port parameters from measured data. Suppose that we again want these Z parameters, and somebody goes into the lab and they say, oh, I'm going to open up port 2 and take some measurements. So port 2 is open circuited. That's just hanging. And I measure V1 to be 8 millivolts. I1 is 4 microamps. And I sub 2, the current, no, what is I sub 2? 0, isn't it? If port 2 is open, I sub 2 is 0. There's no current flowing, and so the only other variable that I can measure is the voltage across that output terminal, which suppose that that ends up being minus 8 volts. That's one set of measurements. I just opened up port 2 and took those three, measured those three values. Now what I'm going to do is I'm going to take port 2 and short circuit it. Now what's V2? It's 0 now, isn't it? So now I can measure the other three. V1, let's say, is 5 volts. I1 is 5 milliamps. And I sub 2 is 250 milliamps. Now you've already told me something about each of these two conditions for these two tests or for these two measurements to have occurred. With port 2 open, you've already told me that that gives rise to this fact that I sub 2 is equal to 0. And now we can go back to our z parameter governing equations, put in I sub 2 equal to 0 into both equations, and see what you end up with. For 1, if we looked at the first equation, that's the V1 equation, we can now find or solve for Z11 using these variables. Z11 is simply V1 over I1 with that output port open circuited, or with I2 equal to 0. We measured V1 to be 8 millivolts. I1 was 4 microamps. So that this ends up being 2K ohm for Z11, or 2,000 ohms. We can also, with I2 equal to 0, or with port 2 open, we can also find or solve for Z21. That's the ratio of V2 to I1 with I2 equal to 0. And this one, if you go through, ends up being a minus 2 megohm. That's Z21. Then we have our second set of measurements with port 2 short-circuited. That now implies that V sub 2 is equal to 0. And now we have a little bit more interesting algebra, maybe, but we could now say, okay, V sub 2 is Z21 I1 plus Z2 sub 2 I sub 2. And we've already found this guy from before, haven't we? Z21. So that now we can solve this for Z sub 2, 2. This now is equal to 0, and we now have minus Z21 I1 over I sub 2, and that ends up being with the measured values for I1 and I2 with the short-circuited second port, or port 2 short-circuited. This is now 40K for Z22. And we could also go back to our first equation. We now have Z11 already determined. We have I1. We don't have Z12, but in that second set of measurements, it really doesn't matter what V2 is. We can now use I1, I2, and V1 to solve for Z12, and Z12 ends up being minus 20. And those are now our Z parameters from a collection of experimentally measured values. We've now found Z parameters by analysis. We've found them by measurement. Now let's use those if somebody now built up a circuit around a two-port, or what might be referred to as a terminated two-port. We now hang a load on V2, and we maybe put an input into the input terminals. We now are going to be looking at terminated, or a terminated two-port network. For example, here is our two-port. with the appropriate V1 and V2, I1, and I sub 2. What we want to do is terminate that, meaning we now want to hang a load onto the output side, Z sub L, some impedance, and we want to drive that with some source that might have a source impedance, Z sub G. And there's a lot of different things that we might be interested in relative to this particular interconnected circuit, a terminated two-port. Somebody might say, well, what's the input impedance looking into those two ports? Or what's the output impedance looking in from the output? Or somebody might say, what's the gain between V sub G and V sub 2? Or what's the amplification of the current between I sub 1 and I sub 2? And we need to find ways of relating those particular parameter values to those desired quantities. What do we know on the left-hand side in terms of relationships between? What we are trying to do is actually find relationships for these voltage gains, current gains, output impedance, input impedance in terms of V sub G, the Z parameters, Z sub G, and maybe Z sub L. We might like to know, how do we relate those to maybe the voltage gain between V sub G and V sub 1? What we can do is we can identify some governing relationships. On the left-hand side, well, we know if we have Z parameters, we know that we have this. We know we have V1 is Z11 I1 plus Z12 I2. And we know V sub 2 is Z21 I1 plus Z sub 22 I sub 2. But what else do we know? We also know how V sub G, V1, and Z sub G are related by the left-hand side. We can now say that over on the left-hand side, we have minus V sub G, just doing a KVL. If I do a KVL, don't let me set that equal. Let's now say that's plus Z sub G I1 plus V sub 1 is equal to 0. What about if we did something similar on the right-hand side? Well, now we can relate V sub 2 to I sub 2 and Z sub L. That's just Ohm's law generalized, except I sub 2 is going in the opposite direction we would normally think of in terms of the passive sign convention. So now we actually have V sub 2 is equal to minus Z sub L I sub 2. Is that okay? So now we have 4 equations. And we might want to find, let's say, the input impedance. Or we might want to find the voltage gain. Or we might want to find the current gain. There's all sorts of things we might want to be doing with this terminated two-port. Suppose we wanted to find Z sub I. And these relationships are all cataloged in one big table in Chapter 18. Let's just show where one of those maybe of the many different possibilities comes from, or how we might derive that. If we wanted to find the input impedance Z sub I that we had just defined, Z sub I is just V1 over I1. That's Z sub I, or Z sub n. That's V1 over I1. And we want to now try to find a relationship for Z sub n in terms of our Z parameters, Z sub G, Z sub L, and V sub G. Those are the parameters we want to use. So now what we want to do is try to get rid of some of these I1s and I2s, V1s and V2s in this relationship. Looking at equation 2, or let's start with equation 1. Let's try to eliminate I sub 2 from equation 1, since we really want V1 over I1, and we have V1 and I1 there. If we could just get rid of or rewrite I sub 2 in terms of some of these other parameters, V sub G, Z sub L, and Z sub G. So let's now try to eliminate the I sub 2 variable from equation 1. To do that, we're going to do it in stages or in steps. We're going to actually start trying to use equations 4 and 2 to find another form that will relate I sub 2 and I sub 1. Do you see that we have a V sub 2 here and a V sub 2 there? So I can get rid of V sub 2, and now I simply have I sub 2, I1, and I sub 2 in one equation. I can now solve that I sub 2 in terms of I sub 1, plug that back into equation 1. That's where I'm headed. Is that making any sense? Let me try to write that down. I'm trying to eliminate I sub 2 from equation 1, and one of the first steps in doing that is I'm going to use equation 4 in equation 2 and solve for that I sub 2. And what it will be in terms of is simply I sub 1, and that's a good thing. Well, we had V sub 2, which was minus Z sub L I sub 2. That was equation 2's left-hand side. But that's equal to Z21 I1 plus Z sub 22 I sub 2. This was just V sub 2, right? And now we have an equation that just involves I1 and I2. Now we can say from that I have minus Z21 I1 is equal to Z sub 22 plus Z sub L times I sub 2. Or I now have I sub 2 is equal to minus Z21 I1 over Z sub 22 plus Z sub L. Now I can use that relationship to eliminate I sub 2. Doing that, I now have V sub 1 is equal to Z11 I1 plus Z12 times what I just derived, which is minus Z21 I1 over Z sub 22 plus Z sub L. Or this is now Z11 minus Z12 Z21 over Z sub 22 plus Z sub L times I sub 1, and that's equal to V1. And that's now going to give me my input impedance, Z sub I. Z sub I is now V1 over I1, so I divide both sides by I1, and I'm left with Z11 minus Z12 Z21 over Z sub 2 plus Z sub L. And that might be one of your expressions in that big table that relates your input impedance to a terminated two-port in terms of Z parameters, load impedance, and potentially input voltage and input impedance. But in this case, we didn't need the input voltage. We're looking for the input impedance, didn't we? That concludes chapter 18. That gets us to the end of the book. And I will see you, if not sooner, I will see you in in a week, isn't it? Today's Tuesday. A week, but much sooner. 10:30 is your final on the 17th. Good luck with your finals.